Okay, so equilibrium vapor pressure, water versus ethanol diethyl ether there. Well, vapor pressure of water is, when the vapor pressure of water equals to the external pressure, the temperature that you reach there is 100 degrees Celsius, much higher than the other two molecules there. Now, this is due to the hydrogen bonding. When you have water molecule, each water molecule can hydrogen bond with 4 other water molecules. Each ethanol molecule can only hydrogen bond with 2 other ethanol molecules. So the more hydrogen bond you have, the more energy you have to use to break those hydrogen bonds, resulting in a higher boiling temperature there. Okay, so that's what we're looking at. And here's a question: combining the gas wall equation, combining the vapor pressure that we talked about here, and we can ask you to do this calculation. If you put 2 liters of water in an open container in your dorm room, completely seal the dorm room, assuming there's no escape of water vapor outside of the room there. Now, if the room has a volume of 4.25 times 10 to the 4 liter, it's a fairly big room there. Now, when the temperature of the room stays at 25 degrees Celsius, how much of that water will evaporate? Well, the water will get into the gas phase, and it will reach the equilibrium when the pressure equalizes with the when the pressure equals to the vapor pressure. So in this case, we give you the density of water at 25 degrees, 0.997. Okay, vapor pressure 23.8 millimeter mercury. Now, how do we figure out how much water can evaporate? Well, pressure is given. Okay, P equals to 23.8 millimeter mercury. V is given 4.25 times 10 to the 4 liter. Okay. R and T, temperature is given. R is a constant, temperature 298 Kelvin, 25 degrees Celsius. Okay. So what we can do here is that using this equation, N equals to PV over RT. Under this particular vapor pressure, we can calculate how many mole of water will get into the gas phase. And if you plug in the number there, and pressure equals to 0.0313 atm, that's the partial pressure, vapor pressure for water at 25 degrees Celsius. Okay, and then we can calculate the number of moles. Number of moles, N equals to 54.4 moles. So basically, this equation, using the gas law equation, ideal gas law equation, we can figure out under this particular condition, about 54.4 mole of water will get into the gas phase. Now, 54.4 mole of water is equivalent to 980 grams. We have roughly about 1,994 grams of water, 2 liter versus 0.997 gram per milliliter. That's 2,000 milliliter there. So this is how many grams of water we have. This is how many grams of water that will get into the gas phase. Well, we can conclude that not all of the water will evaporate under the condition if you completely seal the room with no possibility of water escaping the room there. Only about half of the water will get into the gas phase when the equilibrium is reached. So this is another type of calculation that using vapor pressure we can ask you here. And combining the gas law equation PV equals nRT, you figure out the quantity of the water molecule that will get into, in terms of moles, will get into the gas phase, and then convert them back into mass there, and you can solve this problem. Okay, and now, of course, when you do evaporation condensation, it involves the change of state. Now, what we need you to know is that you need to know the names of the phase change. Evaporation, condensation, you need to know what happens in terms of what state is the matter in before and after those processes there. So, namely, we have 6 different processes there, namely evaporation, condensation, and melting and freezing, sublimation, deposition. We also want you to pay attention to each of the process, the energy requirement for each of the process, whether it's exothermic or endothermic. Now, when you look at these type of things there, when you look at the change of state there, use water as an example. Okay, and think of water. If water goes from liquid to gas, in this process, we call it evaporation or vaporization. Now, when you convert liquid water into gas, you have to supply energy. So this process is going to be endothermic. And then the reverse process, in this case, when you have water vapor condensing back into liquid, well, that's condensation. Condensation is an exothermic process because energy will have to be released. One process, endothermic, reverse process has to be the opposite, exothermic there. Now, liquid water can also get into solid. Well, liquid water to solid water is ice, and so this is freezing. Okay. Now, in the freezing process there, heat is being released. Okay. So this is an exothermic process. Okay. And then in melting, solid water get into the liquid water. This is the melting process. That's an endothermic process. You have to supply heat to melt water. When you hold ice in your hand there, your body temperature, well, you feel it's cold. Your skin feels cold. That's because energy is being taken away from you to melt the solid water into liquid water there. Okay. Now, one situation that does not happen with water is going from solid state directly into gas phase without going through the liquid phase. Now, some of the molecules, some of the compounds will do that. And iodine as an example, iodine, if you have iodine as a solid, room temperature iodine is a solid. If you heat it up, you don't see iodine solid melt into liquid first. Rather, it gets into gas phase directly. So this is what we call the sublimation. Okay. And going through from solid to gas without going through the liquid phase, that's sublimation. And this, again, just like liquid into gas, you have to supply energy. This is an endothermic process. And the reverse process is exothermic, and the term that we use to describe that process is deposition. So if you heat up iodine molecule, and you have a glass of water, and you put some ice in the glass of water, there you have a cold surface. When the vapor of the iodine hits the cold surface, it goes back directly to solid without going through the liquid. So that's a deposition process, and that's an exothermic process. The heat is being released. So this particular diagram basically summarizes the change of state from liquid to solid, to gas, and the energy, the terms that we use to describe those changes there, as well as the energy requirement there. Well, you have to make sure, using water as an example, when you try to figure out whether a particular process is exothermic, endothermic, and then you know water going from liquid to gas, and that's endothermic, and reverse is going to be exothermic. Okay, so the phase diagram is something that we can use to actually describe the condition where a substance changes phases, going from solid to liquid and liquid to gas. And if you manipulate the temperature and the pressure, you will be able to manipulate and the existence, the state, or the state of the existence for different matter there. So there are different regions in the phase diagram. Within that region, a particular pressure and temperature, substance will stay in solid phase. Within another region where another specified temperature and pressure, and the substance will stay in the liquid phase. For the third region there's going to be a gas phase. And so there are always going to be three regions in the phase diagram there. What we want you to be able to do is that when we give you a phase diagram, you will be able to identify which part is the solid phase, which part represents the liquid phase, which part represents the gas phase there. So this is a typical phase diagram. The darker blue side, under this kind of pressure